So we have already discussed in the previous videos that what is a parallel circuit. Now in this video lecture we will be talking about the electrical power in a parallel circuits. So for any parallel circuit, the power delivered to any system will always equals to the power absorbed by the system. So as we described in the video lecture of electrical power in a series combination of resistors, that the power delivered to any system will always be equals to the power absorbed by that system. Now the same is the case for the parallel circuits, that the sum of all the power delivered or absorbed by the system will be equals to 0. Or simply we can say that the sum of all the power delivered to any system will be equals to the sum of all the power absorbed by that system. Now to prove this point, let's take an example in which we have a DC voltage source which is connected in parallel with 3 resistors R1, R2 and R3, and Is is the current through this DC voltage source. And as we described earlier that for any parallel circuit, the current is divided through each path or through each resistor, and the voltage is the same. So the voltage drop across this first, second and third resistor will be equals to as the voltage of this DC voltage source. Now let's say the power delivered by this DC voltage source is PE. The power absorbed by this first component is, let's say, P1. The power absorbed by this second component is, let's say, P2, and the power absorbed by this third component is, let's say, P3. And as we described in the video lecture of electrical power, that power is equals to I into V, where I is the current through a component and V is the voltage across that component. Now here we have another form of electrical power, which is P is equals to I squared into R. So now by applying this concept here, so as we described earlier that the sum of all the power delivered or absorbed to any system is equals to 0. So here we have a DC voltage source which is able to deliver the power, and let's say the power delivered by this DC voltage source is PE, plus the power absorbed by this first resistor is P1, plus the power absorbed by this second resistor is P2, plus the power absorbed by this third resistor is P3 is equals to 0. Now as we discussed in the video lecture of electrical power, that whenever a current is entering at the negative side of any component and leaving the positive side, so that component is able to deliver the power, and the power of that component is negative. So the power of this DC voltage source would be negative, minus Is into E, plus, and we already discussed in the video lecture of electrical power that whenever a current is entering at the positive side and leaving the negative side of any component, so the power at that case would be positive, and that component is able to absorb the power. So in this case the power is positive, so I1 squared into R1, plus the same case is for R2, I2 squared into R2, plus I3 square into R3 is equals to 0. Now move this term into the other side of equation, so we get I1 square into R1 plus I2 square into R2 plus I3 square into R3 is equals to Is into A. Now from this equation it is proved that the power absorbed by any system is equals to the power delivered to this system. This side of equation represents the power absorbed by the system, and this side of equation represents the power delivered to the system. Now to understand this in a more brief way, let's take another example in which we have a DC voltage source which is connected in parallel with 3 resistors R1, R2 and R3, and Is is the current through this DC voltage source, and I1 is the current through this first resistor, I2 is the current through this second resistor, I3 is the current through this third resistor, and the potential difference across the terminals of this DC voltage source is 28 volts, and the resistance value of this first resistor is 1.6 kilo ohms. The resistance value of this second resistor is 20 kilo ohms. The resistance value of this third resistor is 56 kilo ohms. Now if we are asked to find out the total power delivered by this DC voltage source and the power absorbed by these 3 components, and let's say the power delivered by this DC voltage source is PE, and the power absorbed by this first component is, let's say, P1, and the power absorbed by this second component is, let's say, P2, and the power absorbed by this third component is, let's say, P3. Now to find out the total current Is from this DC voltage source, so first of all we need to find out the equivalent resistance of this parallel network. So the equivalent resistance of this parallel network is 1 divided by RT is equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Now the equivalent resistance 1 divided by RT is equals to 1 divided by R1 is 1.6 kilo ohms, 1.6 kilo ohms, plus 1 divided by R2 which is 20 kilo ohms, plus 1 divided by R3 which is 1 divided by 56 kilo ohms. Now after calculating this, we get 1 divided by RT is equals to 6.928 multiplies 10 raised to the power minus 4 per ohms. Now the equivalent resistance from this equation is equals to RT is equals to 1.44 kilo ohms. So the equivalent resistance of this parallel network is 1.44 kilo ohms. Now to find out the current from this DC voltage source, so by using Ohm's law we know that Is is equals to E divided by RT. So E is already we have, which is 28 volts, divided by RT is 1.44 kilo ohms. So the resulting current from this DC voltage source is equals to 19.4 milliampere. So here we have total of 19.4 milliampere of current from this DC voltage source. Now to find out the total power delivered by this DC voltage source, as we know that the power delivered by this DC voltage source is, let's say, PE is equals to Is into E, where Is is 19.4 milliampere 10 raised to the power minus 3, and the resulting potential difference across the terminals of this DC voltage source is 28 volts. 28 volts. So the resulting power which is delivered by this DC voltage source is 543.2 milliwatt. So 543.2 milliwatt of power is delivered by this DC voltage source. Now to find out the power delivered by each component in this parallel network, so let's say the power absorbed by this first component is P1, which is equals to E squared divided by R1. So as we described earlier that the voltage is the same across each component in the parallel network as the input voltage. So the input voltage is 28 volts whole square divided by R1, which is 1.6 multiplies 10 raised to the power 3. So the resulting power which is absorbed by this first component is equals to 490 milliwatt. Now the power absorbed by this second component is, let's say, P2 is equals to E squared divided by R2. So E squared, E is already we have, which is 28 volts whole square divided by the resistance value of this second resistor is 20 kilo ohms. So the resulting power absorbed by this second component is 39.2 milliwatt. Now the power absorbed by this third component is, let's say, P3 is equals to E squared divided by R2. So E is already we have, which is 28 volts whole square divided by the resistance value of this third resistor is 56 kilo ohms. So the resulting power which is absorbed by this third component is 14 milliwatt. So as we described earlier that the power delivered by this DC voltage source will be equals to the sum of all the power absorbed by these three components. So the sum of all the power absorbed by these three components is, let's say, PT is equals to P1 plus P2 plus P3. So the power absorbed by this first component is 490 milliwatt. plus the power absorbed by this second component is 39.2 milliwatt, plus the power absorbed by this third component is 14 milliwatt. So the total power which is absorbed by these three components is 543.2 milliwatt, which is equals to the power delivered by this DC voltage source, which is equals to PE. So from this equation we concluded that the total power which is delivered by this DC voltage source is equals to the sum of all the power absorbed by this parallel connection. So from this example we also concluded that the less is the resistance value, the more will be the power absorbed by that component. The greater is the resistance value in the parallel connection, the less will be the power absorbed by this component. So the power absorbed by the first component, which is having the resistance value of 1.6 kilo ohm, is 490 milliwatt, and the power absorbed by this third component, which is 56 kilo ohm. So the power absorbed by this third component is 14 milliwatt. So now it's all for today's presentation. If you have any doubt, ask in the comment section. See you in the next one.